A very good day everyone. Today I will be presenting on the lead-tin PBSN binary alloy system, which is one of the most important and widely studied alloy systems in materials engineering. Binary alloy systems play a crucial role in materials engineering because they control phase transformations, microstructure development, and mechanical properties of engineering's materials. A binary system consists of two components that interact under different temperatures and compositions to form distinct phases. Understanding these systems allows engineers to predict solidification behavior, control microstructure, and optimize processing technique. The PBSN system is especially important because of its simple eutectic behavior and extensive industrial use. Regarding the importance of lead-tin binary system, the lead-tin binary system is widely studied because it has a low eutectic melting temperature of 183 degrees Celsius. Besides that, its phase diagram is easy to understand and interpret. Furthermore, it is heavily used in soldering, bearings, battery grids, and coatings. By studying the PBSN phase diagram, engineers can relate composition, temperature, and phases to real engineering application and performance. The primary application of PBSN alloy binary system is soldering in electronic assemblies. The key advantage including low melting point, which prevent damage to electronic components, excellent melting ability, and also strong metallurgical bonding. These properties ensure good electrical conductivity and mechanical integrity of solder joints. Beyond soldering, PBSN alloy are also used in battery grids for durability and conductivity, bearings where they reduce friction and wear, and metal coating for corrosion resistance. Understanding the PBSN phase diagram helps engineers to optimize soldering temperatures, reduce defects, and minimize energy consumption. It also supports the development of lead-free alternative, which addressing to the environment. This slide shows the phase diagram of the PBSN alloy system. The key feature of this diagram is the eutectic point, which occurs at 61.9 wetness percentage of tin at 183 degrees Celsius. At this composition and temperature, liquid will transform simultaneously into two solid phases, making it ideal for soldering applications. The PBSN binary system consists of two main components, which is lead, PB, and tin, SN. The lead has soft, dense, and also silvery gray metal. It is highly malleable and ductile. The melting point of lead is 327.5 degrees Celsius, and the melting point of it is 1744 degrees Celsius. For the tin, it is soft, silvery white metal with a blush tint. It belongs to group 14 of the periodic table and historically used in bronze alloys. The melting point of tin is 231.997 degrees Celsius, and the melting point of it is 2270 degrees Celsius. The PBSN phase diagram consists of three main phases. The first one is alpha phase. The lead is rich in solid solution and the tin is dissolved in lead. This phase it is found on the left side of the phase diagram. Second one is beta phase. You can find this phase on the right side of the diagram. During this phase, the tin is rich in solid solution, which will cause the lead is dissolved in tin. The third one is liquid phase. This phase is fully molten alloy. Next, the phase fields include two phase, which is single phase region and two phase region. For the single phase region, it's including alpha, beta, and liquid. For the two phase region, it is alpha plus liquid, beta plus liquid, and alpha plus beta. Temperature plays a crucial role in determining the phases present in the PBSN alloy system. For PB-rich composition, the alloy remains in the solid alpha phase at lower temperature but begins to melt and enter the liquid region once the temperature exceeds 327 degrees Celsius. which is the melting point of pure lead. Similarly, at the eutectic composition of 61.9 weightage percentage of SN, the alloy undergoes a unique transformation where it melts completely at a much lower temperature of 183 degrees Celsius, forming a liquid directly from a mixture of solid alpha and beta phases. As temperature increases or decreases across these phase boundaries in the phase diagram, the alloy experiences transition between solid, liquid, and two-phase regions, which directly influence its solidification behavior, microstructure formation, and suitability for applications such as soldering. Under normal soldering conditions, which are typically close to atmospheric pressure, the effect of pressure on the PBSN alloy system is negligible and does not significantly influence phase transformation or melting behavior. However, at very high pressure, noticeable changes occur in the phase diagram, including an increase in the melting temperature of lead-rich and tin-rich alloys, as well as a rise in the eutectic temperature. This happens because increased pressure favors the formation of solid phases, which are generally more compact and have lower specific volume compared to the liquid phase. Such behavior is explained by the Clapeyron relation, which describes the relationship between pressure, temperature, volume change, and latent heat during phase transformation. Although these pressure-induced shifts are important from a theoretical and thermodynamic perspective, they are not practically significant for everyday soldering and most industrial applications involving PBSN alloys.
Hi, my name is ROMMEL and I'm going to explain about the task 2, which is level analysis and calculation. So, as you can see, we have our phase diagram for level analysis. Before calculating, we have to consider the composition for at 35% weight fraction of SN. Okay, we already marked it in this phase diagram. So, before we calculate it, we have to apply the lever rule. So weight fraction at alpha, WA is equal to S over R plus S. So we can get 26.9 over 16.7 plus 26.9, and then we get 62%. So after that, we have to calculate for the weight fraction of liquid, which is WL equals to, we have to use this formula, okay, 1 minus W alpha. So our W alpha is 62%, which is 0.62, and we can minus it 1 minus 0.62, and then we get 38%. So for solid, we have to apply the lever rule too. So weight fraction at alpha, we have W alpha equals to S over R plus S, which is 62.8 over 16.7 plus 62.8, and then we get 0.79, which is equivalent to 79%. So weight fraction of beta, W beta equals to R over R plus S. So where did we get our R plus S? So this is our R and this is our S. And then we just substitute it in here, and we can get 16.7 over 16.7 plus 62.8, and then we can get 0.21, equivalent to 21%. So for the discussion of the result, why did alpha increase from 62% to 79%? This is because all liquid which is at 62% transform into eutectic alpha plus beta. Eutectic mixture itself contains more alpha than beta. So total alpha is equals to primary alpha plus eutectic alpha. For microstructural implications, the final microstructure consists of coarse primary alpha, grains dominant phase, and fine eutectic mixture, which is alpha plus beta, in interdendritic regions. Thus, the higher alpha fraction, which is about approximately 79%, explain that it has a good ductility and lower hardness than eutectic PBSN alloy. So the phase diagram displays a simple binary system composed of two components, which is lead and tin, which has an eutectic point. The phase diagram plots relative concentration of lead and tin. So along the x-axis and temperature along the y-axis too. The eutectic point is the point where the liquid phase borders directly on the solid, which is alpha plus beta, which represents the minimum melting temperature of any possible lead-tin alloy. Hypoeutectic explains that composition is less than eutectic composition, which is CO less than CE, while hypereutectic shows that composition is greater than eutectic composition. CO is greater than CE. So for the critical discussion, for phase dominance at 35%, which is for SN, the alloy is hypoeutectic, which is below the eutectic 61.9%. So the result shows that the microstructure is dominated by the alpha phase, which is 71.6%. So for the mechanical interpretation, since the alpha phase lead is rich, is significantly more ductile than beta phase, where the tin is rich, this 35/65 alloy will be softer and more malleable than a eutectic solder. For solubility, the fact that both alpha and beta coexist at 150 degrees shows that the alloy has cooled below the solidus line but remains within the two-phase solid region, which is alpha and beta, where the tin has exceeded its solubility limit in the lead. That's all from me. Thank you.
Hi, I am Muhammad Arif Syazani. Moving on to task 3, I will evaluate the connection between the lead tin system and SDG12, which is responsible consumption and production. As you can see on this slide, we are facing a major engineering conflict. Firstly, look at the technical benefit. The lead tin system is technically superior because it forms a eutectic alloy at exactly 183 degrees Celsius. This low melting point means it requires less energy to process and provides excellent soldering connection for electronics. However, we have a serious problem. Lead PB is a heavy metal with high toxicity. Its use and disposal pose severe risks to human health, specifically neurotoxicity, and can damage our ecosystems. This leads to the SDG 12 context. This situation creates a direct conflict with SDG target 12.4, which call for the environmentally sound management of chemicals. As engineer, we are forced to rethink how do we maintain technical performance without violating safety standards. So, how do we resolve this conflict? This brings us to achieving responsible production. The knowledge of binary phase diagram is actually the key solution here in two ways. Number one, innovation. Engineers use binary phase diagram to design safe alternative, known as lead-free solder, such as tin silver copper or SAC alloys. By studying the phase field, we can replicate the good properties of lead solder without using the toxic lead itself. Number two, e-waste recycling. Understanding the melt points, specifically the solidus and liquidus line, allow us recycling facilities to thermally separate valuable metal from rest. This helps us recover materials instead of dumping them. In conclusion, phase diagram analysis is not just a theoretical chart. It is a critical look that allows us to balance high technical performance with sustainable, responsible, and production. Thank you.
In conclusion, the lead-tin binary system, it is a simple eutectic system widely used in soldering. The eutectic point is at 61.9 weightage percent SN at 183 degrees Celsius. For the key findings, level rule analysis for 35 weightage percent SN has alpha phase increases from 62% to 79% after eutectic solidification. For the microstructure, coarse alpha dendrites plus fine eutectic mixture shows that high ductility and lower hardness. And in the engineering insight, lead-tin alloys offer excellent weighting and low melting point for electronics, which in environmental concern, It leads to toxicity and need for sustainable alternatives. Sustainability-linked SDG 12, it promotes lead-free soldiers, same as in the critical discussions, such as SAC alloys, and implement e-waste recycling for resource recovery. That's all. Thank you. In conclusion, the lead-tin binary system, it is a simple eutectic system widely used in soldering. The eutectic point is at 61.9 weightage percent SN at 183 degrees Celsius. For the key findings, level rule analysis for 35 weightage percent SN has alpha phase increases from 62% to 79% after eutectic solidification. For the microstructure, coarse alpha dendrites plus fine eutectic mixture shows that high ductility and lower hardness. And in the engineering insight, lead tin alloys offer excellent weighting and low melting point for electronics, which in environmental concern, it leads to toxicity and need for sustainable alternatives. Sustainability-linked SDG 12, it promotes lead-free soldiers, same as in the critical discussions, such as SAC alloys, and implement e-waste recycling for resource recovery. That's all. Thank you.